Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about science and math. And today we are talking AP Chemistry, Unit 1, aligned with the College Board, Part 2, because we ran out of time last time because I talked too much. Okay, so the very last part of our AP learning objectives is 1.8, valence electrons in ionic compounds. And this is great because this is straight out of Honors Chem. Every single one of you already know this. And see, this just gives you confidence to know how great you are already at it. I think you don't even need me to teach this to you. All right, so valence electrons and ionic compounds. Let me get on the right page here. 1.6. It's right here. Okay, so ionic covalent. Ionic, does it transfer or share electrons? Okay, maybe y'all don't know this. Ionic, does it transfer electrons for an ionic bond, or does it share electrons?
Does it transfer?
What?
Does it transfer?
Yes, it transfers. So for our little learning objective, it just says we have to talk about ionic, but we're going to talk about covalent a little bit too, because you really just can't talk about one without the other one. So covalent share electrons to make a bond, and in particular, they share an electron pair is what makes a bond. Okay. So how does this work? Compounds overall must be neutral. So this makes it easy. All of our math equals 0. We got to make it always equal 0. That makes it easy to do. Okay, so now this is the main thing we're talking about, ionic. What holds ionic compounds together? And it's because opposites, do they attract or repel? They attract. That's why we got a little love here. Opposites attract. Okay, so you have these two ions. Remember, an ion is a charged atom that has gained or lost electrons, and then one's positive, one's negative. They stick together like magnets. So cations and anions, which is which? So everybody look over there next to the periodic table. You see some lovely cats on the wall there. So cats are wonderful, lovely, positive creatures. Now I know some of you are dog people and you're thinking, but let me put it in perspective for you. On the other side of the periodic table, you see a fire ant. And fire ants are terrible, negative creatures. They bite you, it gets infected, it looks like a zit, it really hurts. Some people are allergic to them and have to have an EpiPen. So they're terrible, right? So as compared to fire ants, cats are terrific and positive. We can agree on that, even if we're dog people, right? Okay, so cations are positive. They're to the left of the periodic table, and they are metals. And so these are atoms that lose electrons. Now, why do they want to lose electrons? It's what we talked about before. They all want to be like noble gases, and they want to have a filled outer level where they have 8 valence electrons. And so if they have a few too many, then they'll just lose them, and then what's underneath will have 8. Okay, everybody imagining that? Electrons are negative, so if an atom loses electrons, it becomes positive. Does that make sense? Sometimes I co-teach with Miss Olivier, and she says it doesn't. She says for something to lose but become positive doesn't make sense to her. But she needs to imagine them a little better. Okay, so an anion is on the other side. It's on the right. It is nonmetals over there, and they are negative. So how do these atoms become ions? So lithium. What charge is lithium going to want to have? What? +1, because it wants to lose 1. Now, when we write an ion, we want to be cool like math and have understood ones. You know how you don't write 1x in math, you just write x. So we don't write +1, we just write a plus. It's an understood 1 there. Okay, what will aluminum want to become? plus 3. It wants to lose 3, because if it loses 3, it's going to feel like neon. Do you see that? Lithium, if it loses 3, if lithium loses 1, it's going to feel like helium. So aluminum is plus 3. What about fluorine? What's it going to do? Is it going to lose electrons? No, it's going to gain electrons, right? It wants to gain 1, because if it gains 1, it's going to feel like neon. So it is going to become what charge when it gains 1? -1. And we don't write the 1, because we're cool like math. Okay, everybody good with that? Okay, how about nitrogen? What's it going to become? -3. It wants to gain 3 electrons. So remember, the valence ones are the ones on the outermost shell. How you know how many it has is you count the squares over from the kitty cats. So like lithium has 1, beryllium has 2, boron has 3, carbon has 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. You do not count the transition metals, that square that starts with number 21 over to 30 and down. You skip those. So gallium has 3 valence electrons. Everybody remember that from honors? See, I told you already know a lot of this. Now, how do they get together and form compounds? Cations are always going to be written first in your compound name, and the anions will be second. That's just a little etiquette. So you say sodium chloride, not chlorine sodiumide, right? That sounds all wrong. So it's just cations first, anions second, little thing like that. So if we have calcium and fluorine, so first of all, we got to figure out what their charges are once they're ions. So what charge is calcium going to make when it's an ion? +2. So I'm going to put as a superscript +2. What ion will fluorine make? -1, yes. Okay, so now we check to see if we do this math, if it equals 0. Is 2 minus 1 0? No. If it is, you just write them together. If it was calcium oxide that makes a -2, then you just write them together. CaO, squish them together. Okay? But if it's not 0, then we have to balance the charges. So we've got 1 calcium, and it's got 2 electrons it wants to lose. We got fluorine, and it wants to gain 1 electron. See, it's got 7. So fluorine will take 1 of these electrons and put it right there. Will it take another one? No, it doesn't want to be 9. Nobody wants to be 9. So what is calcium to do? What can it do? Yes? It's going to go find another fluorine. And it's going to make a nice little lattice pattern. And this fluorine will take the other one over there. And now this is going to have none. 8, none, 8. Everybody's happy. Okay? So for every 1 calcium, it takes 2 fluorines for everything to be balanced out. Now, you really don't have to think about this, because how it works out is if you just crisscross the charges, Mr. Meyer used to call it swap and drop. I call it crisscross applesauce. But each of them will get what is the superscript of the other one. It will get it as the absolute value subscript. Now, what do I mean by that? So calcium is going to get this 1 with no negative down here for its subscript, but we don't write 1s. 1s are understood, so we leave it blank. Fluorine is going to get this +2 down here as its subscript with no plus, absolute value here. And there it is. For every 1 calcium, it's 2 fluorides, or fluorine, crisscross applesauce, swap and drop. Okay, everybody remember that from honors? Yay, I knew this would be easy for y'all. Okay, now what about their names? If something is binary, meaning no polyatomic, just bi means 2 atoms stuck together, then you just, how you do the name is you write down the name of the cation, then you first, and then the anion root, and then you put a special ending on it. What's the ending? I-D-E, it's Ide. So it's calcium chloride, not calcium chlorine. It's sodium fluoride, not sodium fluorine. Okay? So what was the name of this one? That's supposed to be a subscript. Word has a hard time sometimes. ALBR. What's the name of that going to be? Aluminum bromide. That's messy. Okay? Now, polyatomic. There are certain anions, non-metals, who form covalent bonds, but then the little lump of them together will get a charge and they will act like an ion. They're called the polyatomic ions. They are on the back of the periodic table. I gave you 20 of the most common ones, and in my honors chem, I made you memorize them. I have learned that I'm mean old Miss Blackburn, and sweet Miss Corn did not make her kids do that. Now, I don't think y'all have to memorize them if you had corn, but you do need to familiarize yourself with them. Make sure you read over that list on the back of the periodic table. As you use them a lot in this class, you'll probably end up memorizing them without even trying. You probably already know that OH is hydroxide. You know, that's so common. Okay, so their names are on a list, and so how you do polyatomic ions is you look them up on that list, and you memorize it, and you just write it down. Okay, so they just have names. Sometimes they're kind of traditional names. Sometimes they reflect the elements that are in them. Sometimes their prefixes and suffixes reflect the amount of oxygen that's in them. More oxygen or less oxygen. Okay, so ancient metals. And I also learned that Miss Corn didn't make y'all learn this either. Ancient metals. Some metals make more than one ion. So like where we had the pattern of the 1, 2, 3 skip, -3, -2, -1 zip, those metals in the middle from the transition metals, especially those ancient ones like iron and some of those like tin, all of these ancient metals, a lot of them don't just have one ion they can become more than one. And remember, chemistry has been around way longer. People have been doing chemistry way longer than the science of chemistry has been around. So people have known about a lot of these ancient metals for a long time. And so these ancient metals that have more than one ion, you can show that by two different ways, okay? So the cation is followed by a Roman numeral telling you which one. So that's one way to do this. Or the cation has a different name based on its Latin name. Now, when I was in high school in the dark ages of the 80s, they told us that the Latin names were going away and it was going to be all Roman numerals. So I didn't bother memorizing my Latin names. That just seemed like a waste. That was not the modern way. Well, they lied. The Latin names are the most common names. The Roman numerals are very rare. This will make it for good video while I wander off and answer the phone. Hello. Hey. I do not mind. Magnets for you. So important, getting a call in the middle of class. Okay, so those Latin names are still around, and you see them more often. You really do not see it just out in the real world seeing chemicals. You don't see any Roman numerals. But for example, iron. Iron can be iron 3, and it has a charge of, yes, you guessed it, +3. Or it can be iron 2 with a charge of +2. Iron 3 is called ferric. Iron 2 is called ferrous. So like you've seen these and not realized it. When you're reading the ingredients on your toothpaste, it doesn't say tin-4 fluoride. It says stannic fluoride or stannous fluoride. See, you've seen them. So they are much more common, the Latin names than the Roman numerals. They tried, but it didn't take. Just like in the 70s where they tried to switch us all to the metric system, and it didn't take. We still have gallons, we still have miles, we still have Fahrenheit degrees. Sometimes they try, and we just don't go along with it. And this is one of those situations. Okay, when ionic compounds form, they are crystals. They make crystal lattices. But just one little unit like sodium chloride is called a unit cell. Now, notice that I drew salt on this. I want to make the point that we think of salt as sodium chloride, right? But in chemistry, we refer to all of these ionic compounds as salts. So we'll say all. They're all salts, okay? Because they make these crystals. So like, they just refer to all of these as salts, ionic salts and stuff like that. They're very stable. Okay, now your standard here, your learning objective doesn't really talk about covalent bonds, but if you talk about ionic, I feel like you have to at least mention covalent so that you can keep it in perspective. So where ionic bonds are between a metal and a non-metal, what are covalent between? Two non-metals, right. So that's one way how you know that something is ionic. And how it makes an ionic bond is it shares an electron pair. So a single covalent bond is one pair, a double is two, a triple is three pairs. Y'all remember that? See, wasn't that easy? All right, so that's it for the video. Science is great. Like, share, subscribe.